should display screen. Are you able to see the screen and my voice is audible?
Yes, sir.
Yes, sir, both are
Yes, sir.
fine. Yes, sir.
Thank Thank you. So let's just summarize what we were doing. We discussed the calculus, or we are discussing calculus of complex valued function of complex variable, which in some sense can be written as two real functions of two real variables. We quickly started discussing about the analyticity or the analytic functions and differentiability. Remember that in a domain, there is no difference between the two, but at a single point, differentiability can be defined for a single point, whereas analyticity can only be defined for a region, howsoever small, around that particular point. And then the rules of differentiation are basically same as the rules of differentiation for the real variables, as long as we understand that the function is analytic in a certain region. We discussed about the entire functions. We discussed that there exist certain points where the function may not be analytic, and we call those points as the isolated singularities. The important condition that we have the limit, which is basically the derivative, for that to exist from all the directions of the Argand diagram or the Argand plane, this del f over del z star is equal to 0, which is basically the complex form of Cauchy-Riemann conditions. We also understand that the functions u and v are called the harmonic conjugates of each other, and because they satisfy Laplace equation uxs plus uyy equal to 0, and the same for vxx plus vyy. We had differentiability under control, analyticity defined in terms of the differential ones. Now we started discussing complex integration. As soon as we come to that, we understood that since we are talking about a path which will be lying in a complex plane, so we start talking about contours. That means that the functions should at least be piecewise continuous on the path of integration. This is very similar to what we define as the line integral. It is just that the complex integration or the contour integration is the complex sum of the line integrals. In order to have association with the real integration, I will strongly advise you to go back and look at your vector integration which you must have done. There also you defined your line integral. Have a look at that. It's very important. In some sense, you can have some connection between the complex integration and the line integration. Where there we were having the sum of the real components, here we are having the sum of the complex terms. In order to have the complex integration about a path, we defined something called a simple closed path. This path may be lying in a simply connected domain, or it may be multiply connected domains. The simplest point would be to understand the multiply connected domains. They are in terms of the holes in the simple connected domains. And what we were discussing towards the end was the path dependence versus path independence of complex integral, where we were using path integration. What was path integration? We were saying that we are parameterizing our z in terms of a real variable t, which will take values between a and b. So the complex integral over the contour c, my last equation, can be written as an integral f of zt with dz over dt times dt. Remember, when we are writing this, we need our function fzt and dz over dt both to be piecewise continuous. And that's what the contour is. That the function as well as the derivative of z with t, that is piecewise continuous. So we were taking an example. We did that part of it. What was the example? That we had two functions, fz is equal to z and fz is equal to real of z. And what we did in the class, fz is equal to z, which was integrated over this contour going from 0, 0 to 1 plus 2i through path c, which is designated as number 1. and through path C1 plus C2, which is designated as number 2. And we got the result that both were coming out to be same. So path integral fz over from 0 0 to 1 plus 2i over the contour C, independent of the path taken, gives you the identical result. And then I came to you basically asking you to do a homework where I asked you to do the same for this real Z. Now, did somebody do it? Did somebody get the result?
Yes, sir.
Yes, sir.
Okay. So what was the result for path 1?
1/2.
1 by 2. And for path 2?
Plus I.
Plus I.
नहीं सर 1/2 ही आया था बस because real part of z था ना so
Yeah, but see, when you are doing function as the real part of Z, I think I will take it up. That means next Monday on this path integral. But okay, let me just tell you. So Z is given as what? Z is given as x plus I y, right? Fz is given as real part of the Z, that is x. But whenever you are going to parameterize Z in terms of t and you are taking dz over dt, that of course has both the component. It is the fz part which does not have any imaginary part portion. Yeah, I mean, if you haven't done it, I will take it not in today's class, but this is something which is the direct result. I mean, this is a solved problem of crazy book. One of the reasons why I gave you so that you just open the book and you can just have a look at that. In case if we have difficulties, of course, I will take it. But the important point which you will see, anyway, somebody said half plus I, and then what will be the result for part 2, B2?
1/2 plus 2I. That's what I.
Half plus 2i.
Yes, sir.
Yeah, in case if you have got half plus 2i and half plus I, this looks reasonable to me. The result is telling you something that this function fz, which is equal to real z, this is path dependent, that it doesn't only depend on the endpoints, but it also depends upon the actual path taken by this contour. Yeah, so that way you have complex functions which are path independent in terms of their integrals, and you have complex functions which are path dependent in terms of these complex functions. So the big question lies, what is the big question? Are there set of complex functions which are path independent? You had that in vectors also, by the way, that path independent functions and the path dependent functions. So you were writing your vectors in terms of gradient of scalar and you were doing something. But okay, here again the question now comes, are there set of functions which are path independent, or do we have to every time solve it in the manner in which we have solved? We'll have to parameterize, we'll have to figure out these paths, and then we just do that. So a big, does somebody remember this, that something comes to our rescue for this answer? No, okay, doesn't matter. Yeah, I am expecting that you had a course on complex analysis. It is just that you will have to review several things. I am not going too much into the theorem derivation. I am into the applications. So we do need to see how we are going to apply it. I will keep on giving you relevant theorems. We may not do any derivation there, but we will keep on applying those theorems so that we understand what we are talking about. Remember, we are going to talk about these calculus of complex valued functions of complex variable. That's the title of the topic, if you ask me. Okay, a theorem which actually comes to for our rescue in this case is a famous Cauchy-Goursat Theorem. Now, Cauchy, of course, is well-known name in complex functions. He has done lots and lots of work. In fact, several formulae are there, whether it is analytic functions, whether it is integration. Cauchy's name exists almost everywhere. But in this particular theorem, which is a very well-known theorem and very important from the point of view of what we are discussing, this guy Goursat also did something. So let's just first read this statement. Let me just write it. Read this statement and then we will dissect it as we do. So if fz is analytic in a simply connected domain, that means no hole, D, then for every simple closed path, remember the simple closed path, C in this domain D, we have fz dz is equal to 0. Now, this is a big result. It will have a lot of consequences, actually plenty of consequences. But let's just remember simple closed path which does not intersect with each other or which does not touch with each other. So that's what the simple closed path was. So if there is a domain, a domain is the one when I'm talking about entire region, and there is some path which is lying inside, then the integral of, if the function is analytic in this simply connected domain, and then for every simple closed path in this D, then the integral over this C is contour is taken to be 0. Now let me say at this point something about the direction of the contour also. It's very common. I mean, it's just that electron is taking a negative charge, kind of common, that whenever the contour is traversed in counterclockwise direction, it is called positive oriented contour. This means that I am going to just go basically opposite to what the clock needles do. Yeah. So this is called positive oriented. So we have a contour line. Now this result will have big impact on whether we can figure out certain functions to be path dependent or not. This theorem comes for a big rescue. Okay. By the way, before proceeding further, if this C would be negative oriented, let's say in this particular problem, that the integral C fz dz is, will that be 0 or not, the result?
0.
Yes or no? I mean, that's
Yes.
okay. So one has said yes.
Yes, sir.
Yes, sir. So remember
Yes,
that when the result is 0, it does not matter whether the contour is traversed in a positive direction or a contour is, let's say if I draw the same contour in the negative direction, because one is negative of the other. This is one of the point which I mentioned during the initial introduction. So if there is a negative oriented contour, which means that the contour is traversed in a clockwise direction, then also the result is not going to change. Yeah. So C prime, because this guy C prime is nothing but the negative of this C, and negative of this integral will still be 0. But this has plenty of consequences. Plenty of consequences. Why? So let's talk about the entire functions. So sin z. What are entire functions? Remind me. Entire functions.
The analytic everywhere in the entire Z plane.
Very nice. Analytic everywhere in the entire Z plane for extending up to or less than infinity. So Z less than, strictly less than infinity. These functions are called analytic entire functions. In fact, I even ask you one question there, that if I try to ask for a function which is analytic everywhere including infinity, what kind of function that could be? Does there exist any function like that or not? Anyway, for this point, okay, I mean, let's just continue with Cauchy-Goursat theorem. And if I ask you, let's say, the integral of sine z, yeah, over any contour lying in z plane times dz, what would be the result? Even without going through any integral.
Zero.
This will be 0, and this C can be traversed positively or negatively, and in fact it is for any simple closed contour lying in the entire region. I mean, it doesn't matter where we are talking about this contour, because it is analytic. Sin z is analytic everywhere up to uh, z is strictly less than infinity. Yeah, the same thing is true for e raised to power z. So think about this function, and if I ask you to evaluate the integral Ez dz, you'll say, okay, sir, this is result is 0 coming from Cauchy-Goursat theorem. Okay, let's just continue to understand and dissect few things about this. How about this now? Dz over z square plus 9 for a contour which is nothing but a unit circle about z is equal to 0. So let's just make it. So we have z is equal to 0. We have a unit circle. So this is 1 and let's just consider positive oriented. So these two things are very important that you should be knowing on what path we are integrating. Now, question: positive oriented unit circle about z is equal to 0 defines my contour C. If I ask you, what is the result of this integral dz over z square plus 9? What will you say?
Zero.
Okay, so you were saying 0, and why would you say that? Because the function is not analytic at z square plus n is equal to 0?
But it is not inside the contour.
But this point is
Exactly.
outside the contour. Yes.
Exactly. Very nice. So as long as this function remains analytic inside and on the contour, we do not need to worry about anything else. Well, in this case, for example, you will have, so 1, 2, let's say 3, so plus 3 and minus 3, you have two singularities, but those singularities are not lying within this contour, inside or any part. So this is x, this is y, and hence you can now quickly started getting the result. Okay, this is about part 1, that if the function is analytic now, you can get the result pretty quickly. Question: is this theorem necessary or sufficient or both? So what is the question? Let me just rephrase it. The condition which I have given you, this fz dz over this c is equal to 0, whenever fz is analytic inside and on this simple closed path, this is 0. Is this mandatory that if and only if fz is analytic, then we will have this result?
If
Or
z is zero, then also.
if fz is not analytic, let's say, can we have a situation where fz is non analytic and we still have this result equal to 0?
Maybe yes, sir.
Sir, if the path are positive and negative and they cancel out.
If the path and positive and negative and they cancel out, how do you
As in
decide on that?
the way in which we are taking the integral, for example, this is in positive sense which you have drawn. So if
Yes.
there is an equal and opposite negative sense
No, no,
which
but
is
you
present.
cannot. I mean, see, when you are talking about a closed path and the simple closed path, I mean, how the simple closed path works, right? I mean, this has
Understood.
to just go in one direction in one sense. When you are saying you are going from one point to another, A to B, then all you are saying in this case, when the simple closed path is that A is equal to A traversed in one direction. You cannot have both the direction traversed together. Yeah,
Okay,
because
so
then
sir,
the integral will
in
not be
that
defined.
case, it won't be zero then if it's analytic,
Yeah,
not
okay.
analytic.
So let's just think about it. And I will give you an example. Actually, you know the result, but I will give you an example and we will do that. So let's just see. Let's say C again, positive oriented, unit circle about Z is equal to 0. In fact, I do not even need to take a unit circle, but let's just start with the unit circle. Unit circle just means that again the same path which I have considering. Yeah. Now first function, is this function analytic or not? Fz is equal to 1 by z square.
So not at no
No.
It is not analytic at
zero.
z is equal to 0. Now we are going to
That is
integrate,
okay.
yeah, around 0. So this z we are considering basically the contour which takes z is equal to 0. So let me quickly draw this contour, and we have this guy there. So now can we do this integral? By the way, this is a simple positive oriented unit circle. So let me just draw the positive oriented one. How do we do these kind of integrals? This is using the polar form, remembering that it is a unit circle which is given. So in general, z is written as z minus z naught is equal to r e I theta, where r is the radius or the modulus of the circle, and theta is the argument. Yeah. Now in this case, since the circle is centered exactly at z is equal to z naught equal to 0, so we have z is equal to, what is the radius of the circle?
1.
1.
One.
So we have z is equal to I theta, where theta, if you just take from 0 to 2 pi, traverse from first quadrant, second quadrant, third quadrant, fourth quadrant, then you should basically get this integral done. So can we just put z is equal to e I theta, dz is equal to, what is dz?
I eat
I theta.
So I
E
e
theta
I
beta d theta.
theta. Now that we know z, we know dz, can we put it in dz over z square and get the result? So can you do that? What will this guy be? This guy becomes theta going from 0 to 2 pi. Fine. Dz is I e I theta.
Sir,
What will be z square?
sir, d theta नहीं आएगा नीचे.
ऊपर. Oh yeah, sure, okay,
हाँ.
that's very nice. Thank you for reminding me. आएगा ही आएगा, वरना इंटीग्रल किस पे होगा? Thanks. dz is equal to I e I theta d theta, and so this dz is I e I theta d theta, and what will be z square? This will be e to I
Right.
theta. Yeah. So what will be this result? You will have I going 0 to 2 pi e minus I theta d theta, and this result will be
0, sir.
this result turns out to be
0.
0. So what does that mean? That we can have certain integrals in which, even though the function is not analytic inside and on the simple closed contour, then also your result can be 0 for the simple closed contours. Yeah. So that's why the condition in itself Is it necessary or sufficient or both?
Necessary.
So if the condition is necessary,
Necessary.
then it has to be there.
So it's
Necessary
sufficient.
Right.
Sufficient.
So this will fall. Let's just say this is the only right answer for this question, that we have a situation or a condition that if fz is analytic inside and on the contour, then definitely it will be 0. So that means that it is there, but there can be other functions also for which your integral turns out to be 0, even though we may not be completely knowing about all those functions. But what we know about from the Cauchy-Goursat theorem, that the condition is sufficient to ensure that the integral turns out to be 0. So whenever a Cauchy-Goursat theorem is written, one has to be clear that this theorem is sufficient condition. It is not necessary condition. So something which is about the, let's say, details of this. So this is a sufficient condition. Okay, let's continue to further dissect. Now, if the path is no longer simple, so Cauchy-Goursat theorem was given for simple closed path. If the path is not simple, then it was shown that even for even if we, yes, consider,
I have some views like the example.
what is that? Yes.
It's a bottom to the right. You wrote three steps. The zero is not equal to or it is or I so can you make me understand it again?
Say it, I could hear your voice almost like piecewise continuous. I'm not able to hear
Yeah.
it continuously. Can you again ask the question?
So bottom to the right, you wrote 2 to 3 equations that z minus zero equals to or e to the power iota theta. So can you make me understand it again? Can you make
Can
me
we
so
again go
understand
through the
it
same
again that
steps
you
again?
read
Can we go through the same steps again?
z minus
Oh yeah, okay. I
the
mean
only
this,
the
oh, this guy,
what
this guy, huh?
it's this equation.
Okay, I mean
Yes,
this
sir.
is what, again, I mean somehow something is like so let's say you have any point z naught, right, in the Argand plane, and you draw a circle around this point with radius r, capital R, let's say. Then how can you write down this equation that the radius remain constant whenever you are going over this whole path and you still traverse the whole path? So in polar coordinates, this can be easily written that z is consisting of all points about the center such that r e I theta. Now you take the mod of this, then the result should be r, and theta is going from 0 to 2 pi. This guy is giving you an equation of circle in complex plane, that when we are saying that we are talking about a path which is which is a circle in the entire complex plane, it is basically represented by this equation, that we are talking about all the points such that mod of z minus z naught is equal to r, which is the radius, and theta is traversed from 0 to 2 pi. So this is basically that collection. Yeah, this is the same collection which we discuss about the wave function when we talk about that there exists a phase factor and how a phase factor is interpreted. That, I mean, you have the wave function which over any point in this phase, they have the same probability density. So this is the equation of circle in complex plane. Do you want to know more than that? I mean, I would request you to go back, look at your BSc level complex book. I mean, this is very simple definition of the circle, right? Z minus Z naught is equal to REI theta.
Sir, I haven't studied like this equation, that equation for complex circle,
You
etc.
haven't studied it, you just go back, you just find it. In case if you do not find it, I will. But I mean, you can see, you take all the z's, z, take all those z, whichever is there, which I am written, and this will give you this circle equation, REI theta. I mean, this is very common way of writing this complex plane one. In fact, when I asked you to do this del f over del z star is equal to 0, remember, and asked you to do it in the complex plane, then this is something which is appreciated even more. I may post something. Let's just continue with this portion. This is the equation of circle. Okay, in complex plane. Let me just write down that then. Okay,
Okay, sir.
equation of circle. Yeah, this is useful, but in plenty of places, even when you are going to do your radius of convergence, etc. in complex Z plane. Yeah, since for small, I mean, I use smaller here, capital R there, but it doesn't make any difference. R, I'm going to take unity because that's what was given in the problem. Anyway, does it affect your result if R is not taken as the unity, by the way? Will it affect the result?
No, sir.
No, sir. So it doesn't affect. Yeah, I mean, ultimately, I'll have to give some path. But the important point, the takeaway point, that the theorem is a sufficient condition. It's not a necessary condition. Okay. Further takeaway points. Now, even if we start talking about path like this, is this a simple closed path? Now, if I draw this C in some domain,
No,
maybe.
sir.
No, sir.
It is not. But if the function is analytic, if fz is analytic in this domain D, then even for any other closed path, it is just, it has to be closed, simple or otherwise. This result is still valid. So even the Cauchy-Goursat proved that this fz dz over a simple closed path has to be equal to 0. But if this path is lying in any domain in which our let's say function is analytic, then the result remains valid. This was proved later. This was not considered part of the theorem, but later on it was showed that it can be done. Again, I'm not going into the proof of this. However, I can ask a question like this, for example, since I'm doing the application. So think about this. Z E Z. Let me give you a function. Z square plus 9 dz. And I ask you this for a path, which is again, let's say, positive oriented unit circle. And then positive oriented this arbitrary curve. So this is my 1, this is my 2. So I am going to do 2 integration. Well, one is for this one, and another one is for this kind of one curve, which is still enclosed. Okay, curve is inside. So let me, this is my C2, this is my C1, and let's say this is something like, okay, plus 1 minus 1. So let's, now I have drawn two paths. One is my C1, which is positive oriented unit circle. So this is Z is equal to EI theta. And another is a very not simple path, not very, it is not a simple path since it is crossing itself. So I ask you to give me result for these two. For positive
0
oriented
for both.
circle. 0 for
0
both.
both.
And why is it so? The first one is coming directly from the Cauchy-Goursat theorem. And second one is what we were discussing here. As long as this path C2 which I have drawn Be it simple or not, as long as it is not passing through any of the singularities, the validity of our Cauchy-Goursat theorem still holds. So this is something which was done afterwards. Now, at this point, I must also tell you that in the Cauchy-Goursat theorem, it was in many books, you will find that it is written as only Cauchy theorem. And we still take it as the same one. Does somebody know that there is a difference? What is the difference that there was an original Cauchy theorem and then Goursat modified it so that the form which I have written, Cauchy-Goursat theorem, is there? Does anybody know the difference? What Goursat added to that? No. Okay. So let me just tell you. The original Cauchy theorem that fz is analytic, that was part of it. Another part was that Cauchy demanded that f prime z to be continuous also over the same path. That fz is analytic and f prime z is continuous. What Goursat did, that he said that it is no longer required that f prime z be continuous. In fact, if the function is analytic, it is actually true that any order will be continuous. But what Goursat did, he said that this condition that f prime z be continuous is no longer needed. And hence the theorem or the statement which I have given here is the statement of the Cauchy-Goursat theorem. Here we do not ask for the continuity of f prime z or f prime z. But okay, these are the details. I'm not sure how exactly did you do it in your BSc. I'm not hearing too many of the solutions which are coming from you. But anyway, I mean, please keep on revising it. We are going to do more examples. So consequences further. If I have a domain, or let's say if I have path 2 points, so z1 to z2, and it is traversed, let's say, in this way. So C1 and C2 are two paths. So what am I saying? Let's say I integrate Z1 to Z2 through C1, or I integrate, let's say, through this path, second path. And I ask you to give me the result. Fz dz, how can I write down in terms of this Z1 and Z2 for any 2 points which are lying there? So how can I write down this closed path in terms of the C1 and C2?
Would be sum of C1 and C2.
Nice. So it is Fz dz plus Fz dz, right? Now this C2 is what? This C2 is traversed here like this, C1 is traversed here like this, right? Fine. This result, if as long as if Fz is analytic on and inside this simple closed path, what is the result?
0.
This result is
0.
So Fz is analytic on and inside this CV the whole path or C1, C2. But what does this have as the consequence? So C1, if you look into this, is saying that we are going from Z1 to Z2 Fz dz. Yeah, through path C1. This guy is Z2 to Z1, which is your path, second one. Yeah, now that I can write down this explicitly also. This guy is equal to 0. So what do we get? We get it C1 Fz dz is equal to minus C2 Fz dz. Yeah, I mean, this is very simple consequence. Now think about it. So if I am taking, let's say, the path from Z1 to Z2, this guy, and I am taking path both traversed in this. So I am now coming up this C2 prime path. And what is this C2 prime path? If you just compare with C2, compare with C2, is it identical or
Minus of C1.
this will be minus of C1? And why did you say that? This is because it is traversed in the opposite direction. So instead of going from Z2 to Z1, we are going from Z1 to Z2. So remembering that C2 prime Fz dz, what result is this? That Fz dz over C1, whether I go from the left bottom curve or whether I go from the top curve, I get the same result. What is this guy? That means what? That
So
the
it is
integral
independent
Sir,
of
is it
path.
path independence which is
Path independent.
Absolutely right. So this is the question which we were trying to ask, that what kind of functions are there which will have integrals which are path dependent or path independent. We said that in general there can be path dependent or there can be path independent integrals. But now we have a definite class of functions. What is this class? Analytic functions, such that the integral of analytic functions, as long as we are going in a analytic region, we have the result which is path independent. It does not matter for an analytic function whether you are going to go from path 1 or path 2 or path 3, they will all give you identical result, and hence they are point dependent and no longer path dependent integrals. So we have a class of integrals which we call as analytic functions. Again, remember the analytic functions, those were important in our differentiation. Here also in integrals, whenever the function is analytic, then you can say, okay, this guy, I can evaluate using any of the path and I know I will get the correct result because these integrals are path independent. Okay, questions up to this point? No. I hope when you will review what I am teaching, you will have questions. In case if it is not okay, let's just see that you are understanding things. Okay, another simple consequence of this. Fundamental theorem of calculus. What was that? Fundamental theorem of calculus. This is whatever I am writing on this screen, but for the real variables, I mean, generally we write that. What is capital F which I have written?
Antiderivative of
Small
Fz.
f.
Integral at that point.
So this guy is nothing but this. If there exists f prime z in general, this is what we wrote for this one. So the integral for this analytic function, since this integral only depends on the points z0 and z1, so that means that if there exists this dfz over dz in general, then you can always write down your result like this because it does not depend on the path, right? And we call this guy f, by the way, by an interesting name. This is the one which relates your integration and differentiation, right?
So it's the antiderivative.
Great. Antiderivative is given for the integral one so that one can think about it in terms of somehow related with the derivatives. This is how actually the whole calculus started coming up. So anyway, I will not go into the detail. However, I am going for a very important statement, and that is statement is this. One, we have already found that if the function is analytic inside and on a simple closed path, then the result is path independent. 2, I am saying that now if the function is analytic on and inside the simple closed path, then antiderivative must exist. This will always happen. It is not that only if the antiderivative exists that I will be able to write. For analytic function inside and on the simple closed path, antiderivatives always exist. This is the consequence of our Cauchy-Goursat theorem. Because integral is only path independent, it will depend on at the values at 2 points. Values of what at 2 points? Values of the antiderivative at those points. Yeah, so now you can do your integrals, analytic integrals pretty easily. So if I ask, for example, give me Ez dz between z is equal to 0 to z is equal to 1. How are you going to evaluate this guy? Is this function Ez analytic between z is equal to 0 and z is equal to 1?
Yeah, yes, sir.
Because
Yes.
this is an entire function, so I do not even need to check. So what will be the result? All I need to think about, what is this guy? What should I write here?
EZ.
So e to the power z.
E to power z, because this is a exponential z. So that means that once I know this, so what is the result of this? What is
Just
the
the
result of
values of
E
e to the power z at
minus
the
1.
endpoints.
e raised to power 1 minus e raised to
Minus
power
1.
0,
0.
which is 1. So e minus 1. So now for certain integrals, as long as the function is analytic, you do not need to worry about doing whole path integration thing which we actually evolved with. You can just directly do the integration as we were doing in certain cases in the real integrals. So this is a important consequence. Okay, let's just see if we have other consequences of. What if I try to apply my Cauchy-Goursat theorem in doubly connected regions? Or doubly connected. Okay, domains, I should reuse the word. Next, and eraser. Okay. So what were doubly connected domains? You have to have how many holes? At least?
One.
Exactly.
Sir, 1.
At least exactly. At least or exactly?
At least.
No, if it is more than one, then I will call it triply connected domains and multiply. So we will extend the result to multiply connected domains. If it is doubly connected, if I am defining the word doubly connected, then you cannot have more than one hole. Okay, anyway, if I try to apply it, now I cannot directly apply it. And then there is a trick. How do we apply it to the doubly connected domains? What do we do? So if, let's just define my question, fz dz. Let's say fz is analytic in the entire domain D, which is lying between C and C1. C and C1 are nothing but the contours, two contours, right? So fz is analytic in the regions between C and C1, but fz is not analytic anywhere inside C1. So I cannot directly apply now my Cauchy-Goursat theorem. So what do we do in those cases? We say that we are just going to basically draw the same guy. I cannot draw it exactly in this manner, but I can try. And I draw something like this. So what have I done? My C is traversed in a manner such that I have a cut, a line joining between these 2 points, and this cut is infinitesimally small. So I can write down my whole integral. So A, B, now coming out to be C, D and A. So look at this. A, B, C, D, A. And also look at the path which I am traversing inside is not exactly the path which was given in my original problem, but it is opposite of that. So let me just write it as C1 prime. So this is what we do. And then we say, okay, there exists some length AB. This I call as gamma 1 and this DC I will call as gamma 2. So that I can write down my entire integral C as the sum of gamma 1 plus C1 prime, since I am traversing now in the clockwise direction, plus gamma 2 plus, and then what? This D going back from A. So this is C. And this result will be what now? Why did I do that? What did I achieve by doing it?
Sir, it will be 0.
Why it is 0?
But, sir, because the domain is now analytic everywhere.
Exactly. So the whole point of making this cut is to ensure that now this path, the whole path A, B, C, D and A, this becomes a simply connected domain. So this guy becomes your simply connected domain. And hence I can apply my Cauchy-Goursat theorem there. So the result should turn out to be 0. And what further? Now this, look at how this gamma is traversed. Gamma is traversed as AB, then gamma 1 was traversed, and how gamma 2 was traversed? It is going in the opposite direction, CD. So what these two guys will be contributing to this?
So 0. They will cancel out each other.
These guys will cancel each other because they are traversed in opposite direction. Yeah. So the result which will turn out to be the integral of C, which was our original contour, fz dz turns out to be minus of C1 prime fz dz, which is basically same as fz dz, but C1 traversed in anti-clockwise. So remember the original problem had this C1 traversed in anti-clockwise. So what did I get in principle? What I get in principle is another very important point in evaluating integrals, that what we call as path deformation. Now what is path deformation I am talking about? Look at the result which we have got. Any arbitrary contour which is given to us, C, which is the outer one. If this function is analytic throughout from C to C1, then I do not need to worry about how complicated my C is. I can always try to build my C1 such that I can evaluate fz dz over C1. So let me just give an example and then you will see. So we talked about this 1 over z squared. This function is not analytic at z is equal to 0. Yeah. So now if I ask you to evaluate this integral fz dz over some arbitrary contour which is like this, but which of course has this guy z is equal to 0 inside it. How will you do that? Because you cannot write your z is equal to e raised to power I theta or re I theta. It's no longer a unit circle I asked for. Now I am asking for a contour C, let's say traversed positively, but it's an arbitrary contour. So what will you do to solve this? You will say that I will use now the principle of deformation of path or path deformation, and I can build any arbitrary contour, which I can even take to be circle. And I will, instead of evaluating over this C, I will evaluate my result only on C1, which is nothing but a unit circle in this plane, complex plane, about z is equal to 0. So what is happening, that look at this 1 over z square function. It does not matter where am I going to take this C or C1, because this function is analytic everywhere between C and C1. And hence I can use the previous point, the path deformation one. I will evaluate for C1 fz dz, and I'll say that the result will remain valid for fz dz over C as well. So what was the result which you got for this guy? So let me say C1 positive oriented unit circle about z is equal to 0. What was the result which we got? We got 0. Yeah. So the result will remain valid for any arbitrary contour, since the function other than z is equal to 0 is analytic. So look at the importance of this path deformation. I do not need to think about a complicated path over or the contour over which I am supposed to integrate. I can integrate on something which I know well, and I know my circles equation very well, and hence I can do this integral. Yeah. In fact, now you can do it for multiply connected regions also, and I am going to ask you to help me write this multiply connected domains. When I am saying multiply connected, basically it can be 2 or more than that. So doubly connected, remember, was this. So let's say there may be many of these holes. So what am I drawing? Let me just first say C and any place between this C1, C2, C3, C4, all of which are holes, such that my function is analytic everywhere else except within the holes, except within C1, except within C2, except within C3 and C4. And I ask you to give me the result fz dz over C. Let's just traverse. Okay, I have traversed it all in the opposite directions. Oh, so I should do it this as well. It doesn't matter. It won't have changed my result, but okay. Can somebody give me this? So what is
So the sum of the integrations over
Sum of the
C1 to
integrals
C4.
over the small regions.
Okay, now this looks like a nice smiley, and I broke the smiley. So let me write down k is equal to 1 to n, which are the number of holes, and then what should I write?
So integration over CK.
fz fz dz integral over ck. So this particular portion, which is the application of Cauchy-Goursat theorem in multiply connected regions, give us further additional power. What is the further additional power? That I do not need to worry about the actual path of the contour. We can define our paths in our own ways, and we can integrate over those. Result will remain valid as long as the function remains analytic in this or every place. So C, okay, C1, C2 now anti-clockwise. So C3, C4, and let's see, my C goes here so that the positive oriented word remains. You can say that you make it negative oriented and the result will still remain valid, but okay, I should do it. So questions up to this point. Let me try to summarize. I mean, since it's coming to 1 hour, so let me just try to summarize what we have done in today's class thus far. So first, we started with this question. can we think about the set of functions, complex valued functions of complex variables, which are path independent? ऐसे कुछ functions हैं क्या? अगर ऐसे functions हैं, तो उनके लिए this theorem, Cauchy-Goursat theorem, becomes invaluable. The theorem says if the function remains analytic inside and on the simple closed path, then we have this fz dz is equal to 0. What we found out that this condition is one sufficient condition for every simple closed path. Later on, it was found out that this remains true even for complicated paths, as long as those complicated paths, which are not simple, they are there within the analytic portion. Remember this 8 thing which I did. This can be extended to multiply connected domains, and there we will use the path deformation. That means that instead of evaluating over a complicated path, I am evaluating over something which I know. It could be a circle, for example, as long as it is continuously deformed to a place in which the analyticity is maintained. We also figured out that for these functions, these analytic functions, the antiderivatives must exist, and hence the integral becomes just the path independent integral. So any integral between z1 and z2 of analytic function fz dz, where z1 and z2 are 2 points lying within the analytic region, that can be written simply as the antiderivative of z1 minus antiderivative of z0, and this antiderivative must exist. So Cauchy-Goursat theorem becomes one of the very important theorem in the complex valued functions integrals. It has plenty of applications for solving problems, because for analytic functions you can solve pretty quickly. For non-analytic functions you can always figure out, for example in this 1 over z square case, you can figure out that what is a simple path which I can make, or what is the simple deformation which I can do, and then I can still evaluate the integrals. So this becomes one of the cornerstones of complex integrals. Questions?
सर
Yes.
सर ये मल्टी कनेक्टेड डोमेन्स में हमें जो C1 C2 है सब एक ही मतलब सर्कल्स लेने हैं C1 हम सर्कल ले सकते हैं C2 पे आर्बिट्ररी शेप ले सकते हैं सब सेम
देखो आप कोई भी see the point which we are trying to emphasize here, there is no need for circle. You can make your square whatever you can. Remember that idea is this: as long as your function remains analytic between the path which you are making, yeah, and between the original path, as long as that is there, because the whole idea is that you have to have a path. When we were discussing, for example, here a b, from b to c, what kind of path it is, I don't care, can be any path, yeah. So it is up to you to make that path.
तो मेरा मतलब था कि एक ही इसमें जब 3 मतलब जैसे डबली कनेक्टेड है
वो कोई सर्कल हो, एक स्क्वायर हो, कोई ट्रायंगल हो, इट डजंट अफेक्ट यू.
एक ही में अगर मल्टी में जैसे एक ही C1
हाँ, एक ही में अगर मल्टीपल हो, that is what I am saying. So I make circle because I know that the circle's equation is easiest for you to form, and this is what we use most of the time. But you can make anything. I mean, okay, yeah. I mean, the way I draw it is because I find that the circle's equations are used plenty of time. But okay, let's say this arbitrary C1, arbitrary C2, arbitrary C3, arbitrary C4, whatever you want to make, this will remain valid. Any arbitrary, forget about circle or triangle or whatever, any arbitrary. Yeah, fine. Yeah, I mean the point was कि अगर complicated shape पे ही आपको integral करना ही है, तो फायदा क्या होगा? Because again you will be figuring out some complicated equation. So that's what I wanted to say. But yes, it is valid for it. Yeah, you are asking.
The only thing which we have to take into consideration is that the singularity lies within the path which we are choosing, inside the inner path.
Very good. Which means that I can only see. This was, if you look into it, the original problem is something like this, that there exists some finite singularities. Yeah, this is what we are going to use in our Cauchy residue theorem. I'm drawing it so many times now that I'm okay. Ultimately, we are going to do this. So if we want to find out the integral like this, yeah, so how to do that? I will keep on finding out integral around this point, integral around this point, integral around this point, integral around this point, which I will call as residue or whatever. And I will say I will just sum of these. and you will get the result, right? So that is the idea. That original path had plenty, original function has isolated singularities which are also existing. That is the idea.
Okay, sir.
Yeah.
So,
Yes.
so we have done a question which has two parts and both have zero answer. Can you repeat that second part?
Question. We both had 0 and have z is square
Sir,
plus
this
9.
one.
Z is square plus 9. This one? This guy?
Yes, sir. It's
Sorry.
second part.
This guy.
Yes.
Yeah. Okay. I mean, I'm going to do that, but can you remind me that, guys, that you had course on complex analysis, right? I mean, it's, of course, you did not review it, so you are just getting those things, but you have done it in this manner only, the one in which I am going. Exactly? No? Yes? Just give me an idea.
No, sir. I haven't.
Yes,
I
sir.
haven't.
Yes, sir.
When you said yes, sir, that means yes, you went ahead in this way, but you haven't reviewed in between, and hence we are going through this, right?
We actually jumped to residue theorem directly. I don't think we did discuss theorem.
Oh, wow. Pretty interesting. You can.
No, sir, we did it. Actually, we did it. Cauchy-Goursat theorem, Cauchy residual theorem, everything we did it.
Okay. Yeah. No, my so my emphasis, remember, it's in 9 classes. We are supposed to go up to definite integrals. We are supposed to cover a lot. Idea was to, of course, do a review of this. My idea, whenever I teach at the postgraduate level, is to tell you the importance of simple points which are written there in the theorem or the language of the theorem, which sometimes we do not invest reasonable time on. So my idea is to explain each point, and we are still able to do some applications. Derivations, of course, cannot be done in 9 classes. It is impossible. But without that, can you try to understand it? A basic idea is that. So that's what I am trying to do. Let's just try to understand this question anyway. Z is square plus 9. Z over Z is square plus 9. So this function, if I write, is this function an entire function, or does this function have singularity?
It has
Sir,
singularities.
has singularity.
Where does it
Plus
have
minus 3
singularity?
iota.
So z is square plus 9 equal to 0. Two isolated singularities, you will find z is equal to plus 3 iota minus 3 iota, right? Now when you are doing this, z plus 3 iota and minus 3 iota, this means what? This means, okay, so this means that if I am talking about any path which does not include this singularity. So I am supposed to integrate over this contour C, which is a positive oriented unit circle C1, right? So this equation which I can write down as Z is equal to EI theta. Does this include this plus 3i and minus 3i? The singularity
No,
inside
sir.
and on. Does this include that?
No.
No. So as far as the path of integration is considered for this function is analytic, right? Within this contour and inside this contour everywhere, right?
Yes, sir.
Right, sir.
And hence you can apply your Cauchy-Goursat theorem, because even though the function has singularities at plus 3i and minus 3i, but these singularities are not coming in the path, and hence the result will be 0. And in this example, I said further that it does not need to be any simple closed path. It can be even non-simple closed path, but as long as it is lying in the region, let's say -1 to +1 or -2 to +2, I mean, as long as it does not include these singularities, it will still give you the same result. That is 0. That you can put the extension of Cauchy-Goursat theorem, which is that even for a non-simple closed path, then also the result remains valid. In fact, I mean, my idea is to give you certain problems there in your tutorials, do something with the winding numbers which we come up with. But okay, at this point, I do not want to talk about that. My concept was that the function, the analyticity of the function has to be checked inside and on the path of the contour. If it includes, of course, plus circle which is larger than the radius 3, or if it is centered at some other point, then there is a possibility then the result is not 0. Of course, for isolated singularity, my result will or may not hold true, right? You got the point?
Yes, sir.
So I hope you understand that I tried to explain 2 points here. One is that since the function remains analytic within the or on the circle or C or the contour C, then the result is 0 because the Cauchy-Goursat theorem valid. And I also further extended that it does not need to be a simple closed path. Simply connected domain it was, but simple closed path it is no longer needed. In fact, we relaxed that simply connected also to multiply connected, and then we got the results like path independence of this. Okay, good. Anything else? Yes.
Yeah, sir, can we just have a short break before we continue?
2 minutes, okay. Let's have, yeah, I have. Yeah, so yeah, you go ahead and ask question, right? I am still there.
Okay, so sir, for given an example that there is a contour C and then there is an arbitrary shape that is partially inside the contour and partially outside, and the function is only analytical inside the contour.
Then
so,
you cannot apply that.
Okay.
Yeah, then you cannot apply that. You okay? I mean, there are, see, we haven't yet done what is branch cut. We haven't done something else. So I would say let's just try to figure out what we can achieve using the Cauchy-Goursat theorem. So the answer for your question is that we cannot achieve anything because there the path is having the integral, oh sorry, singularity, and you'll have to do something in order to take care of that singularity. So I guess your further question would be, can I ignore the path? So if I draw it, because since we are only talking, so let's say path like this, and there exists singularity here, but there does not exist any singularity in this path. Can we tackle it using just I mean considering only this portion and maybe drawing some path like this here? So maybe your further extension of the question would be like this. Is it?
Sir. Yes, sir.
Yeah, but at this point, I think since we haven't done everything, so let's worry about it. But
Okay.
I must say that in case if the path is like this and the singularity lies anywhere else, then the result of this fz will be integral fz will be 0. For this, surely this will be 0. And this is basically understood in terms of that this path, these non-simple path is basically something like it is sum of the two paths, these two, and individually the results is that the result would be 0, and then you are taking the sum of those two and that result will also be 0 as long as it does not include any singularity, isolated singularity.
Okay, sir.
Yeah. You have plenty of other questions. You can have plenty of other questions also. For example, I mean, what about this guy? So I am traversing it, positive oriented, let's say, maybe arbitrary shape, but traverse many times. Maybe 2, maybe 3, maybe. So I keep on traversing. So will the result change for the integral? For the analytic function, you do not need to worry about anything since the result will be 0. For the function which will have singularity, so let's just think about it. So let's say it has a singularity here, and you will start thinking about deformation path, and you make a deformed path which is, let's say, something which is of your convenience. But now positive oriented, and you circle it once, you circle it twice, you circle it thrice, what will happen to the result? Basically, you are taking the same integral one time, same integral second time, same integral third time. So what will be the result of that? So those are other questions which can also come in the mind, that why it is traversed only once. It can be traversed many times. Yeah. Okay. So those questions we'll think and we will try to answer those. Is my 2-minute break over? Yes. 10:19. You guys are back, right?
Yes, sir.
Yes,
Yeah.
sir.
Okay, let me say now that you have questions and I'm seeing that you are interactive also, at least in this portion. I mean, more than one or two people. You read this book. The problem with the book is that this is a book dedicated to complex analysis. Yeah. So it will be, I mean, reading of course, almost an entire book. But the good part of the book is that it tries to explain every time it is coming up with the theorem. What I can suggest you is this: do not go through the entire portion, but try to be specific in terms of, since we are going to be applying it, basically we are trying to evaluate integrals, things like those. So even if you just tackle the theorem and the derivation, not the derivation, but the application, are you able to gauge things out of it? Please understand that the word contour is starting from the word contour to the point where we are integrating. This is more on the concepts being applied first. Once we understand how to apply the concepts, then it is rather simple. I mean, once we understand that, since there are only few theorems, so please go through that, those who are interested. Those who are not, I cannot ask you that you must go through this, because I mean, applications are there in almost every book. You talk about Afghan, you could talk. Afghan is a very good one. Crazy, you take that, you will find plenty of problems there. So I cannot say that you must go through it. However, you will find that the language of the book is better suited for a complex analysis at advanced level as compared to language of any other book. Any other book. This book is. So this is kind of a connect between your undergraduate and the research level work. So it is a basic advanced complex analysis book, I would say. Anyway, so where do we want to go? We want to go to now to the next point, which will be the famous Cauchy's integral formula. In order to reach there, let's just apply first our Cauchy-Goursat theorem, and that is why I think that you must have done your Cauchy-Goursat theorem before you go ahead with anything else. Even Cauchy integral formula, that comes naturally from this application of this Cauchy-Goursat theorem, which is what I am going to do. Question is now pretty simple again. I do not ask for very complicated questions. I want to evaluate this guy. Now, over, it is mandatory, I have to give you something. So let's say a positive oriented, traversed ones, positive oriented, arbitrary shape of contour C enclosing Z is equal to 0. So I am talking about what? I am talking about integrating dz over zn, something like this. Any complicated which includes this z is equal to 0. Now this is of course not an analytic function. So you will have to integrate now. 1. 2. Can you use something from the Cauchy-Goursat theorem to solve this integral? So what is n, by the way? N is integer, positive, 0, negative. That means 0, plus minus 1, plus minus 2, plus minus 3, so on and so on. So I am just going to integrate this. So can we use something from the Cauchy-Goursat theorem?
Firstly, you can take the unit circle instead of C.
Yeah, I can take unit circle, I can take, right, anyone, but I will take a general circle, okay, so that you also have a way of tackling general circles. Now that I have seen that you have this. So I can use principle of deformation of path. Of course, the circle doesn't look like that, but I can evaluate this integral instead over something this, and I will say my result will still be valid. Why my result be valid? Because of the principle of deformation path. So what have I taken? Z is equal to R E I theta. But Z is centered around what? Z is centered around 0. So those of you who are understanding this equation, so this is R E I theta, where R is this and theta is going from 2 to 2 pi. R is of course fixed because it's the equation of the circle. So it is just this. Yeah. What will be dz?
RI theta d
Sir,
theta.
iota r e
di
to the power
theta
I
d theta.
e theta.
So instead I can basically, okay, instead of doing this dz over zn over this original c, I can do this. Now c1, which means theta going from 0 to 2 pi dz I r e I theta d theta, and z raised to power r n e I n theta. So what will this become? 0 to 2 pi, right? And then what should I write? I, okay, fine. I can r raised to power
minus n.
minus n plus 1. Sorry if it is not visible properly, but anyway, minus n plus 1. Then
P raised to power
exponential
minus 1. Iota.
minus n plus 1 iota
Theta.
theta
D theta.
d theta. And what will be the result?
One upon n minus one to the n minus one into r to the power n minus one.
So I r minus n plus 1 over minus n plus 1 and
So
so
that I will cancel out now.
okay, so yeah, I will cancel out, but I am just writing everything explicitly. Does everybody agree with this, the result?
Yes, sir.
Yes, sir.
But what will happen if minus n plus 1 is equal to 0 or n is equal to 1?
So we'll have a discontinuity there.
I mean, see, this integral is solved for different values of n. So it's not about that your integral is over n, right? So we are trying to find out. This result will remain valid for all values of n except for n is equal to 1, right? Yeah, and then what? So you have exponential minus n plus 1 I theta. What will be the result? So it is important to note that this result is valid for all n's except for n equal to 1. What will be the result? 2 pi, and n is an integer. So theta from 2 pi, 0, an integer.
Sir, 0.
Because your theta is over 2 pi and you multiply it with any integer, you are going to again get the integral multiple of 2 pi. You are not going to get any time pi by 2, since it's integer number which is getting increased. So you just put the value of n other than of course 1, and you can do that. But this result turned out to be 0. This is interesting, except for n is equal to 1. So for n is equal to 1, what will you say?
Sir, 2 pi iota.
How did you get it?
Calculation, sir.
Very nice. Excellent. So, okay, so let's just do the same calculation which you have done. So that means that for this guy, we will have to solve it explicitly. Use the same method. So theta is equal to 0 to 2 pi, dz will become I
Z
r
only, iota Z.
I theta. Right. Of course, it will become z and you are just cancelling it, but okay, I will still write it. Yeah. Yes, and the result will be
Iota 2 pi.
Iota 2 pi or 2 pi. What is the, in essence, result which you guys, everybody got it, right? 2 pi I?
Yes, sir.
Yes, sir.
So this guy over any arbitrary circle or contour, any arbitrary, not circle is not an arbitrary one, okay. Any arbitrary contour positively traversed will give you the result 0 for n not equal to 1. So all other n, and give you the result 2 pi I for n is equal to 1. By the way, this is interesting why the result dz over z is not 0 and everything else is 0. It's quite an interesting result. But this result is very important for your Cauchy's integral formula. And this is coming basically directly by applying principle of deformation of path. And hence, when you used your Cauchy integral formula, this result which is central to that Cauchy integral formula, I mean, this is how Cauchy in fact himself worked on that. So is required. In some sense, you cannot avoid it. Yeah. Okay. What if this contour does not include this z is equal to 0? This is this, and my contour is like this. So this is the one which we have done, and let me just remove this star which I have. So instead of doing that integral, the one which we have already taken care of, instead of I do this, so z is equal to 0 and I draw a contour here in this Argand diagram. What will be the result for this? So this result is valid.
0, sir. 0.
0 everywhere, or 0 for n not equal to 1 and there will be some non-zero value?
0 everywhere, sir.
Yeah, so very good. So you got 0 everywhere. So this result will be 0 if C does not include 0. Okay, if C includes 0, but it is traversed in clockwise direction. Say it again. Minus negative of this, and it will be, the result will be minus 2 pi I. Yeah. If C is traversed in anti-clockwise, that is positive oriented, but C is traversed 5 times.
Sir, 5 times the value.
5 times the value. So please see that these kind of questions are just quick questions which are all emanating from this Cauchy-Goursat theorem, but you have to just keep on applying it. Okay, so let me just change now a question a little bit. dz over z minus z naught. Yeah. So this is now I am making a question. So dz over z minus z naught instead of z raised to power n or c positive enclosing z naught. What will be the result? Can you give this result?
Sir, I think the only thing is that we'll have to like take the contour around z equals 0 then. Like
Yes,
one should be
instead of z
included
is
inside.
equal to 0, you are taking now. So what is happening in this case? I am talking about a function which instead of, let's say, is not analytic at 0, you have somewhere, let's say here. So let's say this is my z naught. Yeah. And I am talking about a contour which of course is enclosing this. See, what will be the result? Think about it, what you are going to do. You are going to do exactly what we have done, except that now you are going to apply it the same circle. So z minus z naught is equal to REI theta. Now you are going to apply this guy. What difference it is going to make? What will be the result?
The same result.
So 2 pi
The same
I
result.
for n is equal to 1 and 0 for n not equal to 1, n of course is integer. So I should.
Excuse me, sir.
Yes.
Sir, what we are actually doing by doing this thing, like making a circle around a singularity, are we removing this singularity?
We are not. We are integrating a function. I mean, let's see what is the problem. Problem तो बहुत simple है ना. देखिए, problem है कि मुझे integrate करना है. What this function 1 over z minus z naught raised to power n around a contour C, जो कि एक arbitrary contour है और जो कि positively traversed है. इस इंटीग्रल को सॉल्व करके दीजिए. ये करना है हमें. तो हम ये कर रहे हैं, हम वो नहीं सॉल्व कर रहे, हम सॉल्व कर रहे हैं भाई अपना वाला. हम तो कह रहे हैं कि हम तो एक सर्कल बनाएंगे यहाँ पे, उसको हम लोग पॉजिटिव ओरिएंटेड करेंगे और उस पे सॉल्व कर देंगे और जो भी रिजल्ट आएगा हम कहेंगे वो तो वैलिड है अपने हमारे बड़े वाले सर्कल सी के लिए, नॉट सर्कल आर्बिट्रेरी कॉन्टूर के लिए. ये कर रहे हैं हम. यू गॉट द पॉइंट?
Okay, sir. Okay.
We are trying to evaluate an integral over some arbitrary contour by using principle of path deformation, and we are saying that this will remain valid. Basically, we are going for the Cauchy's integral formula.
And sir, there was one more question.
Okay.
So let's suppose a function is analytic in a let's suppose a unit not a unit circle, a circle of radii 3. So and it is not actually, it has a singularity at the the path at which we are traversing it, like
Yes.
z is equals to 3 iota or ab is equals to plus minus 3 iota as we did.
Yes.
So like will it make any effect on the path? Like will there be any different integral for the path or and the region which it is including?
भाई देखो, हम लोग कॉम्प्लेक्स इंटीग्रल सॉल्व कर रहे हैं. वी हैवंट रीच टू द एंड, वी हैव रीच टू द पॉइंट जहां पे कि हम लोग कुछ इंटीग्रल सॉल्व कर पा रहे हैं. दैट इज व्हाट द प्रॉब्लम इज राइट नाउ फॉर अस. सो we are what we are saying, for example in your question, let's say singularity is here and your path is like this. Yeah. So what to do about this guy?
No, sir. It's not like that. I'm saying that the singularity is on the path on which we are traversing.
Oh, this guy itself.
Yes, sir. Yeah, on the whole path, it is not analytic.
Yeah, it is. So what? इसका मतलब आप Cauchy-Goursat theorem नहीं लगा पा रहे. You won't be able to use the Cauchy-Goursat theorem. You'll have to think about something else then. You got the point?
Okay, sir.
I mean, that means that whatever path you are considering, that you cannot directly apply your Cauchy-Goursat theorem. It requires you to put on and inside everywhere the path. और अगर वो नहीं है तो वो कौन से वाले केसेस हम कर सकते हैं वो भी आपको पता चल गए. तो ये केस अभी हम नहीं सॉल्व कर सकते हैं. You are
okay, sir.
Yeah, so we will go there. But okay, I mean, my previous question brings me, and the reason why we were doing it, to my Cauchy's integral formula, which is a famous formula for solving integral. Now, what does this say? This say, so okay, I should just draw this. Let me just write down. Let fz be analytic inside and on, so on a simple closed contour C taken in positive sense. So if Z naught is any point interior to C, then integral of fz over z minus z naught. So we are still going to solve certain other problems using this 2 pi I f of z naught, where C positive encloses z naught. So what have we done from the previous example? Previous example ही तो नहीं लिख दिया है. So what was the previous example? Look at this. dz over z minus z naught, let's say n is equal to 1. So this becomes dz over z minus z naught. And the result turned out to be 2 pi I. Exactly for n is equal to 1, the result turned out to be 2 pi I. But it did not take care of any other integral जिसमें there is another fz which is analytic everywhere. So if I want to evaluate this kind of integral, where there is this fz which is also added to this dz, can I evaluate it? So Cauchy integral formula is giving you that power now to evaluate some more integrals where fz is analytic inside and on a simple closed contour. So let's just see what we are talking about again. So fz is analytic everywhere, everywhere, including z naught. But the function, whole function, this fz over z minus z naught, this of course has this singularity at z naught. Yeah. Can I get the result of this? And the result is that this can be extended just from the previous case, what we were doing. So 1 over z minus z naught dz, that turned out to be 2 pi I. If you have any fz, so it is 2 pi I times fz naught. This is what the integral result would be. I do not need to worry too much about it. All I need to get the function value at that singularity z naught. Okay, so let's just do an example. Ez over z minus 2. Okay, I have written, by the way, Ez. Okay, z over z minus 2. C, where C is any contour positively oriented enclosing this z is equal to 2. If I ask you, what is the result of this?
2 pi iota exponential power 2.
2 pi iota exponential power 2. And how, I mean, you spoke very fast. How did you do that?
So this formula which you wrote.
Which I wrote. Okay, so this is the power of Cauchy's integral formula, right? What would have been the result if I would have written dz over z minus 2, by the way? Exactly the same, including 2 positive sense.
2 pi iota.
So 2 pi
iota, and this
2
you
pi
would have
iota.
got from the previous one. And what would have been the case if I had written dz over z minus 2 is square?
0.
0.
0. Excellent. Okay, let me just give you one more problem. You are doing your integrals pretty fast. Cos z over z, z square plus 9, C, positively oriented and unit circle about origin. So mod z is equal to 1. Okay, result.
1 by 9.
Sir, 2 pi I divide by 9.
Sorry, 2 pi I.
2 pi I divided by 9. And how did you guys do it so fast? Again, you did cos z over z square plus 9 over z, and you basically had your result, because all you needed to do was to have the integral result 2 pi I cos of 0 and 0 plus 9, which is nothing but 2 pi I over 9. Absolutely right. So see the power of these theorems now, or the formula. Yeah, that you are able to solve certain integrals pretty fast. Why? Because the Cauchy's idea was to start working on the analytic functions and then keep on working further, that even if the singularity is there, then I can tackle that singularity in some sense. Yeah. So if I want to do now, if I say that now that you are doing these integrals so fast, if I give you a problem like this, e raised to power 2z over z raised to power 4 dz c, again positive unit circle. Okay. What to do?
0.
How did you get 0?
Sir, the denominator would be z minus 0 whole power 4, right?
But the denominator is not z, n is equal to 1, right? So you are trying to put the formula as 2 pi I, 2 pi I. Instead of that, you put 0 and then fz naught. Yeah. I mean, what my understanding, what you have done is this: 1 over z4 dz, you know, that is 0. And if I give you any function which is, let's say, analytic everywhere, including 0, and I ask you, you multiply that function by e2z or 2 into 0, something like this. Is it?
No, sir, I thought E2Z is analytic anyway, and Z
Everywhere.
1 by Z, yes, and 1 by Z power 4 DZ would give us 0. So I thought
Yeah,
it
so
was
1 by z d4 will give you 0, and e to power 2z is analytic everywhere, and you are applying some sort of Cauchy's formula. But Cauchy's formula was the not the let's say the extended one. It's the Cauchy's integral formula, the extension of that, which gives you the result. And what is the extension? That comes by doing something simple. Writing, okay, first my fz, for example, is, okay, remembering that this is what we are doing, and the reason why I'm doing it, I will also make it pretty clear. So 2 pi I, or writing this as fz is equal to 1 over 2 pi I, wherever my handwriting goes beyond legibility clause, you just remind me. I have used s instead of z because in principle I am always doing my dummy integral. But writing in this form will tell you that if I take f prime z, what will be the result? Remembering that my differentiation and integral orders can be interchanged. Okay, this guy is supposed to be integral. This is positive enclosing z. So if I do f prime z, what is the result? One over 2 pi I, then fs ds
F by
with
s minus z the square.
any sign, positive, negative. So fs, okay, s is equal to s in my handwriting. Okay, yeah. Yeah, so this can be used to extend the power of Cauchy's integral formula, and this is what is considered as the extended Cauchy's integral formula, which I am going to write. Integral formula which says that Fn at, let's say, point z naught, so this is the point z naught, will be equal to n factorial over 2 pi I. You basically keep on differentiating, will fz dz z minus z naught n plus 1. Please see, the only reason I introduced s, because many times when I was writing my fz naught and I was asking students to differentiate with respect to z, they of course keep on differentiating with the first variable instead of the second one. So that was the only idea to tell you that in principle, whatever is coming inside the integral, they are dummy variables. I could have used any notation for that, as prime, z prime, whatever it is. So that was the only idea. But this is the formula with the notation such that f0 z naught, f0 z naught is nothing but your f naught itself, and n 0, 1, 2, so on and so forth. This is the form which you use in general for the Cauchy's integral formula. It is actually Cauchy's extension of the original integral formula to tackle the problems like the one which I have given you, e raised to power 2z over z4 dz. Now, please attempt the same problem. Now, this problem, please write down somewhere, this same problem using your Cauchy's integral formula.
So it's 8 by 3 pi iota.
She did pretty fast. I mean, somehow I find that you are doing integrals pretty fast. So it is because you have done a lot of practice, or what? This is what you have done in your BSc, right?
Yes, sir.
Okay, yeah. Okay, so let's just do that. Others, how are we going to do that? So what is Z naught in our problem? Next.
0.
0.
Thank you. 0. F, what Z you want to evaluate?
4.
So look at the
Z.
formula again. So it is n plus 1 here, and here it
Derivative.
is n. So which derivative
3. That
you want to? So you want to
Third
go
derivative.
for F3Z, which means F1, 1, this you want to evaluate, right? Now, what is your function Fz? It is E2Z. So what is the third derivative?
8 e power 2z.
8 e power
2z.
2z. What is the value of this at z is equal to 0?
8.
8. So precisely this is what you are trying to do. Look at this. Now Fz dz over z minus z naught n plus 1. So you have written that, and what are you going to do? So let's just write it down. E to z dz z4. So we are getting now, go to full result, 2 pi I over 2
n
pi
factorial.
I over n factorial. That means
3 factorial.
3 factorial. So here the result was what you have already got?
8.
8. So what is the result now?
8 by 3 pi iota.
So this is okay, 2 pi I 8 over 6. So 8 over 3 pi iota. So you now got the result. Please see that when you are applying this formula, please see when you are applying this formula n factorial over 2 pi I, this factor you must take care of. If you do not, then it is going to create problem. It is just that in terms of the final result, you may have those issues. But what we have now done after Cauchy-Goursat theorem is to extend the power of evaluating integrals like this to the integrals like fz dz over z minus z naught n. So this fz is added. This fz has to be analytic in the entire region. The function which is integrand, that means the whole of this is of course not analytic, and you have this singularity z naught. But you can use this Cauchy's integral formula or the extension of the Cauchy's integral formula to tackle integrals of variety of functions now. One, analytic, result is always 0. Two, non-analytic, isolated singularities, you can use your principle of deformation of path, and then you can actually solve it. And finally, you now do not need to do anything. I mean, in terms of even remembering Cauchy-Goursat theorem, and several of you, when you were saying that you did not remember, and you basically started by doing Cauchy's integral formula, because now, I mean, I can ask you if you know your Cauchy's integral formula, and I ask you to do this dz over z minus z naught directly. See, enclosing positive, enclosing z naught. So you will say, sir, it is 2 pi I function value at z naught. Right? I mean, this is how you can solve it. But what is fz here in this problem?
1.
Cauchy's integral formula. Go back. What is fz? The fz over z minus z naught dz is equal to 2 pi I times f of z naught. What is fz? In the problem which I am giving you now.
1.
Z is 1. So what is fz naught? It doesn't matter where you are finding out that. It is 1. So the result will be 2 pi I directly, and you have got the result. What will be the result? Dz over z minus z naught cube, for example. For this problem, you have to take the derivative of fz how many times?
Twice.
Two
Two
times.
times.
Two times. So that means that the result
Two
will be
times.
right. The result will be 2 pi I 2 factorial
0.
f double prime z naught. What is the result? F double prime z naught.
0.
Zero.
Zero.
0. So this will be turn out to be 0. So I can understand that several of you who remembers Cauchy's integral formula, they basically remember this result and hence they can solve all those problems which were done using Cauchy-Goursat theorem. The idea of the deformation of path etc. was not exactly required because that is already central to it. The way this formula was derived, the formula had that point central in it. It was derived using the knowledge of Cauchy-Goursat theorem and hence that's inbuilt. So several of you might not remember your Cauchy-Goursat theorem, but I can tell you that that is the theorem which is used for deriving your Cauchy's integral formula, and the extension of the Cauchy's integral formula is then straightforward, just taking the derivative and remembering that derivatives and integrals can be interchanged. So that's in essence what we have done up to now. Okay, another 5 to 7 minutes, I will just explain few more things. Yes, questions on Cauchy's integral formula, Cauchy's extension, and whatever we have done. No questions. So application of Cauchy's integral formula. Okay. So what I wanted to say further about this, if there is one particular formula which is of so much importance, to the complex analysis or the integral part of the complex analysis, I will put that as the Cauchy's integral formula. I wouldn't do it as the Cauchy's residue theorem, even though it will be very, very useful further in evaluating your integrals. I mean, we are going to do that. But Cauchy's integral formula and the extension of that is one of the most important items. I did say about the Cauchy-Goursat theorem the same thing. Cauchy-Goursat theorem becomes the base, and on to that base, it I mean basically built something like this. So on a something like a plain and simple dough, you build your pizza out of that. So something like that. But anyway, bad metaphor. Coming back, Cauchy's integral formula becomes so important. Why? First, it says that if f is analytic in domain D, then its derivatives of all orders are analytic in D. You see that we did the extension, we did not say anything about the domain, we did not do anything else, we just kept on differentiating and we kept on getting the results and we got this f and z. Now, this is what is also making your complex analysis different from the real analysis. Something which I said in the beginning, that complex function, if the function is analytic, then I do not need to worry about the analyticity of any further order. If f is analytic, then f prime, f double prime, then f triple prime, all orders are analytic there. That's coming from this complex integral Cauchy's extension of the integral formula. Morera's theorem. You may have heard of it or not, but it is the inverse of Cauchy's theorem. Cauchy or the Cauchy-Goursat theorem. Okay, I should continue to write that. Now, what does this say? That if f is continuous in a domain in domain D, and your fz dz is equal to 0. So if f is continuous and integral of fz dz over this simple closed path lying in this domain D is 0, then this function is analytic. So that is why it is inverse of our original theorem. But it also gives the definition of analytic functions from the integral point of view. You got the definition of analytic function from the differential point of view or the derivative point of view when you were doing the derivatives. Here, if the function is continuous and if fz dz is equal to 0, then this function is analytic. This is basically the definition of analyticity in integral part. Okay. Fundamental theorem of calculus that arise from this. Liouville's theorem, Cauchy's inequality. If you just go even by the Shom series book and you read your Cauchy's integral formula and then you look at the consequences of the Cauchy's integral formula, you will find plenty of those written there. Those plenty of it, that is the definition of the analyticity of the function from the integral aspect or others, they are all being coming from the same formula. And hence I find that this formula, if one remembers it, and one remembers the way we have arrived at it, then one does remember a lot of things about the complex analysis. Integrals, of course, are slightly, I mean, you have already seen that it is not exactly following the real integration pattern. But this one word, that if the function is analytic and all orders of the function are analytic in the same domain, then that particular sentence in itself takes the essence of the analytic functions in complex valued functions of complex variables. So with this point, I do not want to dwell further on it, since our idea is to keep on applying it. So try to do as many examples as possible. And now I will give you one homework, which is a simple one, which I have already given you, but you will have to keep in mind what we have done may be useful for that. I asked you a question: if the function is analytic in z plane including z is equal to infinity, what kind of function that can be? That you can think about now from this perspective after we have gone through this Cauchy's integral formula. We are trying to look for some function which is not only analytic in z plane, entire finite z plane, but also up to z is equal to infinity. Fine. I mean, we will try to look for that function.
Sir?
So that's the homework. Yes.
Sir, in Morera's theorem, it's claiming that if we satisfy both the conditions, then the function should be analytic, sir. But in one example, we saw
1 over
that
z square. Yeah, but 1 over z square is not continuous.
Okay, sir.
Yeah, this guy, na?
Yes,
so if
sir.
you look at this, if you include any path which includes z is equal to 0.
Yes, sir.
Then that function cannot remain continuous, right?
Yes, sir.
So that's the problem there. Yeah. You're okay. That is why this continuity word is added there. In fact, I told you, remember that Cauchy did his problem by saying that if f prime is continuous and fz is analytic, then this integral is 0 to begin with. So that f prime is, when he said that he is assuming that this f prime z is continuous, he did not even need to think about it. Why? Because when f is analytic in domain D, then all of its derivatives are also analytic in that same domain. So it is inbuilt in this f, in some sense, that if f is analytic, then f prime is also analytic in the same domain. So he did not need to assume it. So see, I mean, the Goursat, of course, explicitly do all the calculations and said that you can drop it. But if one understands the complex analysis, then f prime is continuous. What does that mean? Ultimately, it is about talking about the analyticity of the further orders, and further orders are also analytic. So in some sense, Cauchy did not think that. He wrote it like, assume that f prime is continuous. There is no reason for f prime to be continuous in assumption. It is continuous because it's analytic in the same, f prime is in the same domain. Yeah. So please do as many numericals as possible. I mean, I would say, because most of the time we have asked in the past basically questions, applied questions on these things. Even though my idea or emphasis is more on telling you the concept. Yes.
The Cauchy theorem doesn't say anything about continuity, na? It only tells about differentiability of the function.
Yeah, but differentiability requires continuity, right? And
Yeah.
analyticity requires differentiability. So original Cauchy, when he thought that let's assume that f prime be continuous, so he was thinking about this theorem in terms of the fz is analytic, fine, but what about f prime z? Maybe it is analytic, maybe it is not. To begin with, he started by saying and assume that f prime is continuous, and the derivation is done like that. Right. In fact, I mean, if some of you remember that you might, I mean, not remember, go back, revisit your definition. I mean, how this was derived. I can just give you a hint that the way you derive it, you use famous Green's theorem there. Del P over del X plus del Q over del Y dx dy. This is, oh, so this is R double integral and a contour binding this area. This is p dy minus q dx. This you can write down. This is famous Green's theorem. You use that. And for Green's theorem to be used, you need your del ux and del uy to be continuous. And that was the reason why he used the function to be continuous. Remember that f is equal to, I am going a little bit faster than what I should be doing. F is equal to u plus iv. So if I'm saying f prime, that means I'm talking about del u over del x, del u over del y, del v over. Yeah, I'm just going to say that, but you have next class. So remember when I'm saying that Cauchy-Goursat theorem, we did not prove it in the class. If you look at the proof, you will find that it will be done using this Green's theorem, which is a famous theorem. And I'm pretty sure that you must have used it in your vector analysis, the famous Green's theorem, Swarm series, for example. But I mean, this Green's theorem, this formula which we are using here, the Green's theorem formula, and then you, instead of using this p and q, which are any arbitrary function, you will use your complex functions f, u, and u plus iv or so. So when I am writing del p over del x, you can think about that we are thinking about del u over del x, del u over del y, del v over del x, del v over del y, and then we just put the Cauchy-Riemann condition, and we will show that for the analytic function, this integral turns out to be 0. This is how Cauchy's theorem is proved. I mean, if you look into the book. But for that to be proved, Green's theorem is used. Green theorems require this continuity of f prime, basically. That del u by del x, del u by del y, these are continuous. This is a simpler proof. The Goursat did the tougher proof, where he did not assume that these are continuous. He basically did a proof without using that. But in the books, I'm pretty sure that you must have done. I just go back and look at this, whether you use, Green's theorem to prove it or not. Okay, this is something extra. I mean, I'm not saying that all of you must look into it, but those of you who are interested in understanding the concept, please do not just leave the concepts like that. These concepts are the ones on which whole of the applications are built. If I miss my concept, then I miss my application. Or I would say the power of that concept is what is required. Science is one generation is the technology of next. Why? Because science is based on concepts. Technology is based on science. So as long as the concepts are there. Anyway, I cannot take more of your time. We will start from this point in tomorrow's class. Fine. So we'll start from questions and I will summarize and then we'll go ahead. Okay, bye guys.
Thank you, sir.
And those of you who could not figure out the last part of my discussion, please feel free to ask me. Please feel free to ask me in my Teams chat account. Feel free. Yes.
Off topic बात करते हैं
हाँ बताइए.
I need suggestion on a book for particular topic on like transformation of coordinates. तो मुझे उसमें ना
transformation of coordinates or transformation of random variables भाई.
नहीं इस मतलब इससे related
general one. देखो अगर आप let me just say it like this. अगर आप आर्फकेन की बुक पढ़ते हो, आर्फकेन ने यही करके बुक लिखने की कोशिश की थी. I mean, the original idea of the Arfken's book was exactly like this, that it will try to bridge between undergraduate and postgraduate. I mean, in some sense, graduate portion. Whereas Swarm series books are written in terms of applications mainly. फाइन. तो अगर आप शॉम सीरीज की बुक पढ़ते हैं तो देयर इज नथिंग रॉन्ग. इट इज जस्ट दैट शॉम सीरीज की जो बुक्स हैं वो एप्लीकेशन पे या फिर न्यूमेरिकल सॉल्व करने में इतना ज्यादा बिजी हो जाती हैं कि we lose track of the concept which we try to understand. It's not that वो concept लिखे नहीं हुए हैं, but वो concept इतने intermingled हैं उन problems के बीच में कि one tends to forget it because one is solving all the problems. Arfken is written in the manner in which it is trying to write down not only the concept, it is trying to give you example. So I, for one, recommend Arfken for almost every topic. It is just that it may not be sufficient for all the things which we are doing, but it is a very good book in terms of preparing for your examinations. Yeah. The other two books which people, I mean, I'm pretty sure by this time you also know. One book, of course, is Boas, B-O-A-S, Boas Mathematical Physics book. It's little bit at the starting level. I wouldn't say that it is as good as Afghan for me. But there is another book called Hassani. I mean, there is a book by Hassani and there are two books by him. Those books are also good, but I cannot keep on asking you to read so many books. If you want particular suggestions from me or advice from me, since I do not want to give it to all of you unless until you are interested, as I have been saying about the books all the time, so write to me explicitly and I will explain why I am recommending one particular book. अगर आपको ऐसा लगता है कि आपको किसी टॉपिक के लिए कोई बुक फॉलो करनी है या कुछ और ज्यादा अच्छे से समझना चाहते हैं, कभी कुछ प्रॉब्लम्स करना चाहते हैं, कुछ और, so please do ask it in my Teams account. I will keep on saying it. Issue is कि जब मैं बहुत सारे लोगों को एक साथ एक बात बोलता हूँ, तो they take it very differently. Whereas I want to explain further beyond what I want to say because it does require you. अगर आप नेट की प्रिपरेशन कर रहे हैं या नहीं कर रहे हैं, दो अलग बातें हैं. And hence people read it in different ways. I would say अगर आप कोई भी basic preparation करना चाहते हैं किसी भी level की, keep a copy of the Arfken, whether PDF or whether a hard copy, doesn't matter. Just keep a copy and try to go through the concepts there and even the unsolved if you can.
Okay. तो मतलब मेरा बेसिकली मतलब ये था कि जैसे कोऑर्डिनेट सिस्टम होता है जिसमें हम एक्स एक्सिस को 30 डिग्री से रोटेट कर दें, ठीक है?
हाँ, बिल्कुल सही, मैं समझ गया.
आज की बेसिस पे तो ये हसानी मतलब मैं बुक प्रेफर कर सकता हूँ.
हाँ, आप कर सकते हो, पर अगर आप आर्फकेन पढ़ रहे हो और आपको आर्फकेन समझ में आ रही है तो why wouldn't you first go through आर्फकेन?
उसमें आपके में सब ये सर मेरे को नहीं लगा ऐसा.
हाँ, आप फिर लीनियर अलजेब्रा, दिस इज व्हाई आई आस्क्ड दिस क्वेश्चन. अगर आप लीनियर अलजेब्रा स्पेसिफिकली बात करोगे, आई वुड से देखो अभी हम ग्रुप थ्योरी में फिर से थोड़ी सी वो वाली बात करने जा रहे हैं, रोटेशंस. बट ऐसा तो सोचना बहुत मुश्किल है कि जैसे बालाकृष्णन की बुक बहुत अच्छी है, बट देन सोचना ये मुश्किल है कि आप सबके सब वो लोग वो फॉलो कर पा रहे हो या नहीं. एंड देन आप लोग अगर डिसअपॉइंट हो जाओ या फिर सिंक्रोनाइज में नहीं हो बुक्स के साथ, तो आप वो पढ़ोगे नहीं, सब्जेक्ट ही नहीं पढ़ोगे, दूर हो जाओगे उस सब्जेक्ट से. आई डू नॉट वांट दैट टू हैपन. Yeah. So I would suggest one book if you want to read Afghan. If you want a specific other book, हम लोगों ने Afghan, Kreyszig and बालाकृष्णन का combination लिखा हुआ है कोर्स के लिए. So you can just make a combination of that. And plenty of students are following Shom series. Linear algebra में Shom series मुश्किल हो जाती है because हम लोग inner product का notation different use करते हैं. But other than that, I mean, you can just follow those. As long as you are able to follow it, it is fine. नहीं follow कर पा रहे हो, ask questions. हम लोग हैं, बैठे हुए हैं कि सर कहाँ मिस कर रहे हैं हम लोग, क्यों नहीं समझ में आ रही है वो चीज. दैट इज व्हाई टीचर्स आर देयर, तो वी शुड बी एबल टू हेल्प यू आउट. यप. ओके.